Hello everyone, in this section we have limit and continuity in higher dimensions. Definition: we say that function f of xy approaches limit L as xy approaches x naught, y naught, and we write limit as xy approaches x naught, y naught of this function f of xy, it is equal to L. If for every number epsilon greater than 0, there exists a corresponding number delta greater than 0 such that for all x, y in the domain of function, absolute value of f of x, y minus L less than epsilon whenever square root of x minus x naught square plus y minus y naught square is between 0 and delta. So here on this part we have open interval, because we don't have equal to on this part. In a limit definition, delta is radius of disk centered at x naught, y naught. So here is center. For all points x, y, so for example here in this case we have this point within this disk, the function value is f of x, y lie inside the corresponding interval, which is this part, and that is so L is between L minus epsilon and L plus epsilon. So here our limit is inside this interval, and that is open interval. Now in this part we have properties of limits of functions of two variables. The following rules hold if L, M, and K are real numbers, and limit as x and y approaches x naught, y naught of f of x, y equal to L, and limit as x, y approaches x naught, y naught of g of x, y equal to M. Number one, sum rule. Here we have limit as x, y approaches x naught, y naught of f of x, y plus g of x, y. So here we have plus, we're going to use what we had on this part and add here. So we have L plus M. Now difference rule. We're going to have exactly the same as what we did on number one, but instead of addition we have subtraction. So limit as x, y approaches x naught, y naught of f of x, y minus g of x, y, it is equal to L minus M, because we have subtraction, so on this part use subtraction. Number three, constant multiple rule. Limit as x, y approaches x naught, y naught. So here we have constant k times f of x, y, it is equal to k times limit of f of x, y based on what we had here on this part. It is L, so multiplied by L. So this k is any number. Number four, product rule. Limit as x, y approaches x naught, y naught of f of x, y multiplied by g of x, y. So here we have multiplication. We're going to use, again, what was given, L and M, but here multiply. Number five, quotient rule. Limit as x, y approaches x naught, y naught of f of x, y divided by g of x, y equal to. So here we have division, L divided by M. M is in denominator, and denominator shouldn't be equal to 0. So here M is not equal to 0. We cannot have 0 in denominator. If we had 0 in denominator, that means this is undefined. Number six, power rule. Limit as x, y approaches x naught, y naught of f of x, y to the nth power, it is equal to. So what we had for limit of f of x, y was equal to L. So use L, and here power, it is n. So I have n here as a power, and n is a positive integer. Number seven, root rule. Limit as x, y approaches x naught, y naught of nth root of f of x, y, it is equal to nth root of L. So this is equal to L, power is 1 over n. So n is positive integer, and if n is even, we assume that L, it is greater than 0. Example, find limit as x, y approaches 0, 0 of x squared minus xy divided by square root of x minus square root of y. If we directly substitute x equal to 0 and y equal to 0 in this equation, we will have 0 minus 0 divided by 0 minus 0. So that will be 0 over 0. And this is indeterminate. And again, because of having 0 in denominator, we cannot use quotient rule. So I'm going to rewrite what we have here on this part and multiply numerator denominator by square root of x. Here we have subtraction, so here I'm going to use addition. And this is equal to limit as x, y approaches 0, 0. So here I multiply what we have in denominator, square root of x times square root of x. Here we have x, then we have square root of x times square root of y, and negative square root of y times square root of x, so that part is 0. And finally we have negative square root of y multiplied by square root of y, so it is equal to negative y. So here we have x minus y in denominator. And on top I factor out x, so this part, what we had in common between these two terms, it was x, so I factor out x, and that is x times x minus y, and we write this part. Now here we can simplify, so we can cancel this part, x minus y divided by x minus y. So here is 1, here is 1. So this is equal to limit as x, y approaches 0, 0 of x times square root of x plus square root of y. Now substitute x equal to 0 and y equal to 0. So here we have 0 times the square root of 0 plus square root of 0, so this is equal to 0. We were able to cancel factor x minus y because y equal to x is not in the domain of function. So here on this part, this is our final answer. The surface graph shows that the limit of the function must be 0 if it exists. Now here example, find limit as x, y approaches 0, 0 of 4x y squared divided by x squared plus y squared if it exists. We first observe that along the line x equal to 0, the function always has value 0. So here I substitute 0 for x, and this is when y is not equal to 0, because here in denominator we don't want to have 0. And along the line y equal to 0, the function has value 0 when x is not equal to 0. So if the limit does exist as x, y approaches point 0, 0, the value of limit must be 0. Let epsilon greater than 0. We want to find delta greater than 0 such that absolute value of 4xy squared divided by x squared plus y squared minus 0 less than epsilon whenever square root of x squared plus y squared between 0 delta, or 4 times absolute value of x times y squared divided by x squared plus y squared less than epsilon whenever square root of x squared plus y squared between 0 delta. Since y squared is less than or equal to x squared plus y squared, 4 times absolute value of x times y squared divided by x squared plus y squared, this is less than or equal to 4 times absolute value of x. So based on what we had here on this part, here we had y squared less than or equal to x squared plus y squared. If I divide by x squared plus y squared both sides, This part cancels. So here we have y squared divided by x squared plus y squared. It is less than or equal to 1. So use this part, which is here. And that part is less than or equal to what they have here, less than or equal to 1. I'm going to erase this part. And then next step from here, this is equal to 4 times. Instead of absolute value of x, I can use square root of x squared. And this is less than or equal to 4 times square root of. Here again, we can use x squared less than or equal to x squared plus y squared. So this is the same as what I did on this part. So if we choose delta equal to epsilon divided by 4 and let square root of x squared plus y squared between 0 delta, here we have absolute value of 4x y squared divided by x squared plus y squared minus 0 based on what I have here. And that one was less than equal to what we had here on this part. It is 4 times square root of x squared plus y squared. And then this is less than 4 times, using what I have here, square root of x squared plus y squared, it is less than delta. So here we have 4 times delta, and that is equal to 4 times, based on what we have here, it is 4 times epsilon divided by 4, and this is equal to epsilon. So this means absolute value of 4xy squared divided by x squared plus y squared, it is less than or equal to epsilon. And from definition, we have limit as x, y approaches 0, 0 of this function for x, y squared divided by x squared plus y squared, it is equal to 0. Definition of function f of x, y is continuous at the point x naught, y naught if f is defined at this point x naught, y naught. Limit as x, y approaches this point x naught, y naught of f of x, y exists. And limit as x, y approaches this point x naught, y naught of f of x, y, it is equal to f of x naught, y naught. Function is continuous if it is continuous at every point of its domain. Continuity of compositions, if f is continuous at this point x naught, y naught, and g is a single variable function continuous at f of x naught, y naught, then composition h it is equal to g of f defined by h of x, y, it is equal to g of f of x, y is continuous at this point x naught, y naught. So in this part here, if it is inner function and g is outer function. Show that f of xy equal to 2xy divided by x squared plus y squared. And the point xy is not the origin, so here we have xy is not equal to 0, 0. And f of xy equal to 0 at this point origin. So xy it is equal to 0, 0. It's continuous at every point except the origin. So when the point xy is not the origin, so it's not equal to 0, 0, this function is defined at every point. So to show that the function is not continuous at the origin, we need to show that the limit as xy approaches 0, 0 of our function f of xy does not exist. We are going to approach the origin along the lines of the form y equal to mx, because if the limit existed at the origin, you must get the same value for the limit in order of which curve we approach the origin 1. So I'm going to evaluate the limit as xy approaches 0, 0 along y equal to mx of our function f of xy. So this is equal to limit as xy approaches 0, 0 along y equal to mx of this function to xy over x squared plus y squared. So now substitute y equal to mx here in this function. So this is equal to 2x instead of y. Now here we have mx divided by x squared plus mx squared, and this is equal to 2m x squared over x squared plus m squared x squared, and that is equal to 2m x squared. Now here we have common factor, it is x squared. So x squared times the factorate, and we have 1 plus m squared. This is equal to, we can simplify, so cancel x squared. Here is 2m over 1 plus m squared. If we substitute different values for m, we're going to have different values for the limit. For example, if m equal to 0, limit as xy approaches 0, 0 of f of xy, it is equal to 2 times. So that's instead of m, now here we have 0 divided by 1 plus 0 squared. So this is equal to 0. And if m equal to 1, limit as xy approaches 0, 0 of f of xy, it is equal to 2 times 1 divided by 1 plus 1 squared. So this is equal to 1. This means for different values of m, we get different values for the limit. So by definition, the limit does not exist. So the limit changes with each value of the slope m, based on what we have here for y equal to mx. M is a slope. The limit fails to exist and the function is non-continuous at the origin. To pass tests for non-existence of a limit, if a function f of xy has different limits belong to different paths in the domain of f as xy approaches x0, y0, then limit as xy approaches x0, y0 of f of xy does not exist. Examples show that the function f of xy, which is equal to 2x squared y over x to the 4th power plus y squared, has no limit as xy approaches origin 0, 0. So if the limit did exist, we would have to show that at the point x, y approaches the origin along any curve, we must get the same limit value. But here in this case, limit does not exist. Let's find two curves that as we approach the origin, we end up having different limits. So first, let's look on the curve y equals to x squared. So limit as xy approaches 0, 0 along y equal to x squared of 2x squared y over x to the 4th power plus y squared. This is equal to 2x squared times x squared and divided by x to the 4th power plus, now here instead of y we have x squared, and this is equal to 2 times x to the 4th power divided by 2 times x to the 4th power, and this is equal to 1. Now along the curve y equal to minus x squared, limit as xy approaches 0, 0 along y equal to negative x squared of our function 2x squared y over x to the fourth power plus y squared, it is equal to 2x squared times negative x squared over x to the fourth power plus negative x squared to the second power, and this is equal to negative 2x to the fourth power over 2x to the fourth power, and this is equal to negative 1. So along two different curves, we have two different limits. So this means the limit does not exist.